Last time in phase equilibria, I reviewed TXY and PXY diagrams, including how to draw them and how to use them. I also showed you that sometimes TXY, PXY diagrams can look weird because the system has an azeotrope. So I'll go through those in a little bit more detail. I wanted to go back and revisit the interactions between the molecules that lead to these TXY, PXY diagrams shapes. First, consider an ideal system. So for example, N-butane and cis-2-butene. And imagine a mixture that just has N-butane molecules in it. So we'll start with a liquid mixture and we'll imagine the interactions that are going on between these molecules. So these dashed lines are not hydrogen bonds. I'm just drawing these to demonstrate how, or imagine how these molecules may be interacting with each other. Now, if you were to replace this middle N-butane molecule with a cis-2-butene molecule, would there be any changes to the interactions? Just by looking at the shapes of the molecules, you would say probably not. So the fact that there's a double bond here really doesn't change anything in terms of electronegativity, in terms of overall composition, in terms of overall shape. So N-butane and cis-2-butene are both 4 carbon chains. The only difference is there's a double bond and not really much else. So again, if you imagine how these things are interacting with each other, it doesn't matter whether or not this middle molecule is an N-butane molecule or a cis-2-butene molecule. And what the TXY diagram tells you or shows you is what the bubble point and the dew point is for any composition of mixture. So remember again that at the edges, I have the pure component boiling points. So this is T boiling point for butane there. And this is the boiling point for cis-2-butene. Notice how the bubble and the dew points are always between these 2 points. So they're always between -0.5 and 3.5 degrees Celsius. So take, for example, let's say I had a mixture of 40% cis-2-butene at 0 degrees C initially. This is going to be in the liquid region. And now imagine I slowly heat this mixture up. Let's say we'll heat it to 0.5 degrees Celsius. Now imagine if the mixture were 100% N-butane, the mixture will have already boiled. So this point at 0.5 degrees Celsius is above the pure component boiling point for N-butane. But we don't have pure N-butane. We have 40% cis-2-butene, 60% N-butane. So if we look at what the bubble point is, the bubble point occurs at about 1 degree Celsius, and that is almost the weighted average between them. So again, for ideal mixtures, we oftentimes say that any thermodynamic property is a weighted average. Temperature is a little bit different. It's not an exact, it's not a straight line that's occurring between these 2 boiling points, but it's an approximation. So if you think about what's happening when we are heating this mixture up, we are giving these molecules more energy. So upon heating, molecules gain energy. And at a certain point, the molecules gain enough energy that they start to break away from each other and they start to boil and go into the vapor phase. So at a certain point, they have enough energy, gain enough energy to break away from one another and vaporize. That's what the enthalpy of vaporization reflects, the amount of energy that you need to convert some liquid molecules into vapor molecules. So in phase equilibrium, we have a word that describes that phenomena. We call this the volatility. The volatility of a chemical is the tendency to evaporate or vaporize. So we're talking about 2 molecules that are ideal when mixed. oftentimes, if two substances are very close enough to assume that the interactions between them are ideal, you also assume that the volatility is very similar. So the closeness of these curves in the TXY diagram reflects what's known as the relative volatility. So how close these two curves are together reflects the relative volatility between them. Volatility. If two components are very close, we say that their volatilities are very similar, whereas if the curves were very far away, you would say that the relative volatility is large because one molecule is much more volatile than the other. So if we imagine heating a mixture that is, let's try and make this a more representative mixture. So here is a 40% cis-2-butene mixture, 60% N-butane mixture. If we heat this up to the bubble point, what will the composition of the vapor be? Well, because the interactions are so similar and the volatilities are also similar, so the difference is only 5 degrees C, then the vapor phase is going to be approximately equal. Vapor phase will be similar in composition. So similar, but not exact. And that is what allows us to perform separations. We'll get into this in a lot more detail next semester in composition. And by how much? So similar, but not equal in composition. That's where you can turn to the TXY diagram to tell you. So let's say we heat this up to, we're gonna have to be a little precise here, maybe zoom in a little bit. So let's say we heat it to 1 degree Celsius, then maybe a little bit greater. We'll say we'll have 41% cis-2-butene and 37% cis-2-butene staying behind. So which one is more volatile? It is the N-butane. We say N-butane is more volatile because its boiling point is lower. So did I say that backwards before? So in the gas phase, in the vapor phase, I should have more N-butane, which means I'll have less cis-2-butene. So this 37%, yep, it's where you intersect the dew point curve is your vapor phase composition. So in this example that I just said, the vapor phase composition is 37% cis-2-butene. And therefore the other 63% is N-butane. And the liquid phase composition is 41% cis-2-butene and 59% N-butane. So again, in the vapor phase, my N-butane is enriched. So I have 63% as opposed to 60 that I had before for N-butane. Now again, for this particular example, the compositions of the vapor and the liquid phases are not all that different because the molecules are so similar that their dew point and bubble point curves are very close to each other. So typically that'll be the case. Again, if you have molecules that are close enough in interaction to assume ideal, then you probably have close enough to not have much difference in volatility between them. Now, what about an azeotropic system? Let's talk about how much sense that makes. So here is an example for the ethanol benzene system. And when we look at this TXY diagram, we notice that the pure boiling point for ethanol is down here at 78.2 degrees Celsius. The pure boiling point for benzene is about 80.1 degrees Celsius. So you'd imagine that in a mixture between them, you would think that the bubble point and the dew point should always be between 78 and 80 degrees. When we look at the experimental data for the TXY diagram, we see that is not the case. Instead, the azeotrope, remember the azeotrope is where these curves come together. It is where the liquid phase composition is equal to the vapor phase composition. The boiling point of the azeotrope is 68 degrees, which is below both pure component boiling points. So why does that make any sense? Azeotropes occur. So let's look at the molecular structures between ethanol and benzene. So if you imagine ethanol in a mixture with itself, so ethanol is an alcohol group with 2 carbons. And you imagine the interactions that these ethanol molecules are having with each other. Ethanol is an alcohol, so in this case you will have hydrogen bonding. So remember, there are 2 electron pairs on each one of these oxygens, and it's pretty electronegative. Right, so these electron pairs are going to be looking to bond with something, and these hydrogens are slightly positively charged because the oxygen is going to pull these electrons away from the hydrogen. So this slightly charged hydrogen is going to make hydrogen bonds with oxygen molecules in other ethanols. So you can imagine that ethanol kind of likes to attract itself to each other. So there are attractive hydrogen bonds. Attractive hydrogen bond forces in between ethanol molecules. So you imagine that if you wanted to boil pure ethanol, you would have to give the ethanol enough energy for it to overcome these attractive forces. So in the liquid phase, molecules are close enough to have these hydrogen bonds, but in the vapor phase, they're further apart and you don't have as much hydrogen bonding owing to the distance between the molecules. So you have to heat the ethanol up to a point at which you're overcoming these hydrogen bonds that are transiently occurring. So remember, hydrogen bonds aren't very strong. They're just kind of these slight attractive forces in between molecules. Now let's say that you introduce some benzene into this mixture. So that is the other component of this. Now what is benzene going to do? Is there going to be any hydrogen bonding between the benzene and the ethanol? There's no electronegativity in benzene. So these H's that are attached to the benzene molecule are not very positively charged because the carbon hydrogen bond is not very electronegative. So if you're trying to imagine any bonding between the ethanol and the benzene, it's probably not going to happen. So I have a goofy movie analogy for this. One of my favorite movies when I was growing up was Mean Girls. I really like that movie. So in that movie, there was a group of 4 girls who were very exclusive with each other. They were the title of the movie was Mean Girls. It was about them. So ethanol is like the Mean Girls, or the plastics is what they're called in the movie. So the plastics had these inside jokes that they would tell with each other. They'd be a very close-knit group, but only when they were together amongst themselves. If you introduced outsiders, like in the movie, there were a couple other characters who were not as popular, and they tried to talk to the plastics, and the interactions didn't go very well. So there's repulsive forces that are going on between the benzene and the ethanol molecules that are similar to that movie. So when you look at the TXY diagram, you notice that mixtures of benzene and ethanol, so let's pick a mixture that's 50-50. You think about what its boiling point is. The mixture is much more volatile because the bubble point is less than the pure component boiling points. So in practice, a mixture is more volatile. A mixture of ethanol benzene is more volatile than either pure component. And you can think of this as because, and this is something that's, again, not exactly completely correct, but it helps you to envision what's going on, because it doesn't take as much energy to volatilize this mixture now. Like ethanol and benzene molecules want to be far away from each other, want to naturally repel each other. So therefore, it takes less energy to tear them apart or get them to vaporize. Takes less energy to pull them apart. I'll put pull in quotation marks. Pull them apart. So therefore the boiling point is lower. So azeotropes are more common than you would think. Most binary systems actually do form an azeotrope. So that's actually the norm. Actually, ideal mixtures are the oddball. And most times you'll see the same phenomenon occurring where molecules will have some attractive forces within each other, but then repel other molecules. So this is an example of what we would call a minimum boiling azeotrope. Minimum boiling because, as the TXY diagram shows, the azeotropic composition, or the azeotropic bubble point and dew point is below both pure component boiling points. And that is true for any composition. So even at, say, 10% benzene, 90% ethanol, the bubble point is 72.8 degrees C, which is still below 78 and 80. And that's true no matter what the composition is. Even though minimum boiling is more common, there can also still be a maximum boiling azeotrope. So I'll show you an example of what that one would look like as well. So in this example, I've got acetone and trichloromethane. So let's look at the molecular structures between acetone and trichloromethane. So try to imagine what type of interactions are occurring between acetone molecules. Unlike ethanol, even though there's an oxygen and a couple of electron pairs on each one of these oxygens, there's not going to be any hydrogen bonding in between them because this H that is in this on these carbons is not electronegative. So the carbon is not going to pull electrons away from the hydrogen enough to make it a vaguely positively charged molecule. So there are no hydrogen bonding in acetone molecules. Not much H bonding between them. Similarly, in the trichloromethane, we've got highly electronegative chlorines, but again, the bond between the carbon and the hydrogen is not very electronegative. So there's nothing to, the chlorines, just because it's a carbon-hydrogen bond, you have to consider that these highly electronegative chlorines are going to pull the electron density away from the hydrogen. So we've got a partial positive charge on this hydrogen, but there's nothing for it to hydrogen bond with. So it's not going to hydrogen bond with other molecules. Or not as much, right? Because chlorine is going to have a full octet and there's no spare electrons out here to hydrogen bond with. So not much hydrogen bonding in either of the pure components. But if you mix them together, what happens? So now let's imagine we've got an acetone next to a trichloromethane. And now you've got the partially negative charged oxygen, the partially positively charged hydrogen on the trichloromethane. And now you've got hydrogen bonding that's occurring. So this is a bit of an oddball case where you have two chemicals that are not very attractive with each other, but are attracted to each other. My weird movie analogy for this one is like Step Brothers. So that was another fun movie from my childhood. Step Brothers. So in this movie, John C. Reilly and Will Ferrell play two kind of oddballs, Brendan and Dale. And by themselves, they're very awkward, not very friendly or socially, not very sociable. But then about 20 minutes into the movie, they realize that they are best friends. And they have this iconic scene where they say, "Did we just become best friends?" And they say, "Yup." So when you mix them together, initially they might have some aversion to mixing, but then they realize that they are actually two peas in a pod and they like to bond with each other. So what is this going to mean for our mixture? That this is why it's a maximum boiling azeotrope. So maximum boiling because interactions with each other, molecular interactions are attractive. Are attractive in a mixture. And this means that you need more energy to pull them apart. More energy or a higher temperature to pull them apart. So hopefully this video gives you some physical basis or some understanding about why these weird azeotropic systems occur. Next video, I'm going to do an example problem on how you would use an azeotropic TXY diagram.